Hi everyone, my name is Madeline Howell. I'm a final year PhD student here at Monash University. And I'm going to mix things up for my talk, and I'm going to talk about how we measure red giant branch mass loss in globular clusters with asteroseismology. So you've probably all heard about globular clusters before, but I really wanted to impress the importance of using these objects as test beds. So globular clusters, or GCs, are gravitationally bound groupings of stars where all the stars are born out of the same cloud of gas. And for this reason, we say that they're relatively simple stellar populations. And I'll explain later why I've got that word relatively there. But simple stellar population means that all the stars are coeval, so they have the same age, where we see globular cluster stars as being very old. They're isometallic, so the same metallicity. Because of their old age, they're all metal poor. And we also see stars with similar initial masses, again, due to their old age, where they all have low mass. And GC stars have a typical mass of 0.8 solar masses. Finally, cluster members are found in a variety of evolutionary phases. And because of these reasons, globular clusters are ideal objects to study stellar evolution. And one of my favorite quotes about these objects are that they are the closest approximation to a physicist's laboratory in astronomy. So there's two types of globular clusters. Type 1 are your classic GCs, so basically what I was explaining before. So they have homogeneous heavy element distribution, i.e. isometallic, and we currently don't know how they form. But by studying them, we could determine not only their own formation, but also how our Milky Way formed or other galaxies formed. We also have this second type, which are also referred to as ion complex, and that's because they have non-homogeneous heavy element distribution. So we see a variation in ion and S process abundances. And there is a strong theory for how type 2 globular clusters formed, and it is that they are the likely leftover nucleus of stripped dwarf galaxies. So within my PhD, I have studied 4 globular clusters. 3 of them were type 1, so your classic globular cluster, and 1 was a type 2. So stellar mass loss for low mass stars. For my globular cluster type stars, majority of the mass loss is actually on the red giant branch, where they can lose about a quarter of their total mass. This RGB mass loss is thought to be metallicity dependent, so metal poor stars lose less mass compared to their metal enriched counterparts. And that is something that I did want to test within my study. And one thing I want to emphasize is that mass loss rates remain a major uncertainty in stellar modeling. And this has obvious impacts on any study that uses mass loss as an input or uses stellar models as an input, for example, galactic chemical evolution and population synthesis. And because of this, it is really important that we measure an accurate integrated mass loss on the red giant branch for low mass stars. And as Simon alluded to in his talk before, the best way to measure individual masses is using asteroseismology. So asteroseismology is the science of detecting oscillations that propagate within the interiors of stars, and it's described in terms of spherical harmonics. So we have two main modes that we measure. There's the gravity modes that propagate within the cores and radius zones of stars. And then there's the pressure modes that propagate within the convective envelopes of stars. And it's the convection that is actually driving the excitation and damping of those oscillations. So unfortunately, with the quality of data that I have, I'm not able to detect G modes. So I'm just going to focus on P modes today. Other names for these pressure mode oscillations are acoustic waves. And if we're looking in sun-like or red giant stars, they're also called solar-like oscillations. So to actually measure solar-like oscillations, we take a Fourier transform of either a spectroscopic or a photometric light curve. And they appear as these comb-like Gaussian-shaped structures. And I show an example of a solar-like oscillation for a main sequence star there on the screen. Now there's 2 global asteroseismic parameters that we measure from the solar-like oscillations. The first one is nu max, and that is the frequency of the maximum acoustic power, and that's illustrated in purple. And the other one is delta nu. And this is the large frequency spacing between adjacent overtone oscillation modes. To put that more simplistically, it is the frequency difference between peaks that have the same spherical harmonic L mode. And that's illustrated in red in the inset. Now, pretty amazingly, both of these global asteroseismic parameters are correlated to stellar properties. So nu max is related to the surface gravity and temperature of a star, and delta nu is correlated to the average density of a star. So if we take these two relations and combine them with the Stefan-Boltzmann luminosity law, we can derive a seismic mass scaling relation, which is in terms of nu max, luminosity, and temperature. And this is the actual relation that we use to derive individual masses of stars. So I just wanted to briefly talk about this because I think it's a good visual. So for my study, I was using K2 data, which is Kepler's second mission. And I wanted to compare the K2 photometry to other telescopes. So this is a fantastic image of one of my clusters, M80. This is from the Hubble Space Telescope. It is so beautiful. It's one of the reasons that I love globular clusters. And this is the view in Kepler. A little different. I guess the obvious things are the pixels are a lot larger. You can still tell it's a cluster though. You can kind of see the overdensity in the center. But this kind of shows that one of the major parts of my study was actually making sure we weren't getting contamination from neighboring stars. So we had to make sure that we're only getting an isolated signal from an individual star, and we weren't possibly combining signals. But once we've done that, we can go ahead and measure the masses of red giants. So for majority of my clusters, they're too faint to detect oscillations on the horizontal branch. So we only measured seismic masses in the red giant branch and also the early AGB. And I show, again, this is the same cluster as I just showed. This is M80. And I've got a CMD there over on the left. On the right is actually showing the individual masses. So you've got mass on the y-axis and magnitude on the x-axis. And to actually measure the stellar mass loss, we were using the average masses. So we aren't able to detect a mass loss rate with this method, but instead we measure the integrated mass loss, which I denote as delta M. So we take an average mass loss in both of those evolutionary phase and then find the integrated mass loss. We just take the difference. It's very simple. One caveat to this is because we weren't able to detect solar-like oscillations in the horizontal branch, this integrated mass loss includes both the red giant branch and horizontal branch mass losses. But horizontal branch mass loss is thought to be insignificant, so it is a good proxy for RGB. And here are my results for my 4 clusters. So in this plot, I show mass loss on the y-axis and metallicity on the x. And basically, we wanted to measure a mass loss metallicity trend for low mass metal poor stars. In the background, I show some previous mass loss metallicity trends. They're either dependent on models or one of them actually use dust measurements, which I know is fantastic or is a fantastic tool for AGB stars. But unfortunately, these low luminosity RGB stars that were measured don't have a lot of dust production. So there is uncertainty in the background trends, but I included them just as a comparison. Now to focus on the colored points, these are my actual mass loss measurements. And one thing you'll notice is that there's an outlier. So up the top, we've got M19, or the mass loss for M19, which is our only type 2 globular cluster. And from our results, it's suggesting that type 2 globular clusters actually have larger mass loss on the red giant branch, which was unexpected. And it also suggests that type 2 globular clusters might need their own mass loss metallicity trend. So to keep it simple, I only measured a mass loss metallicity trend for type 1 globular clusters. So I ignored M19. And derived this relation. I'm not going to read it out. You can all read it yourself. So this is a mass loss metallicity trend for type 1 metal poor globular clusters, so less than solar. And there is a couple of other caveats to this mass loss metallicity trend. Again, the first one's quite obvious. It's only based on 3 data points. We would like to populate this plot further by having mass loss measurements in other globular clusters that sample that entire mass loss range, that entire metallicity range. However, that requires more data. But hopefully the upcoming Roman-based telescope will provide us with more globular cluster data that we can actually continue this investigation on. Another thing you can notice is my trend in black has a gradient that's a lot steeper compared to the background trends. And my theory for that is that it's because we're measuring that RGB plus horizontal branch mass loss. I mentioned that horizontal branch mass loss is thought to be insignificant, and we found evidence of that for my most metal poor cluster, which is the red point, or M80. However, we actually found the opposite for my most metal rich cluster, M4, which is the yellow point. M4 is one of the closest GCs to us, making it quite bright. We were able to measure horizontal branch masses. And because of that, we're able to not only measure the RGB mass loss, but also the horizontal branch mass loss, which was found to be quite significant. So here we could be at the metal rich end, we could be having the contribution from both RGB and horizontal branch mass loss that's actually making that line steeper than it probably should be. Ultimately, to resolve this, we need more data, like most issues need. More long baseline data and also bigger telescopes to actually measure the asteroseismology of faint targets. But this is the first modelling independent mass loss metallicity trend. So now I want to jump into a different topic and talk about the multiple populations in globular clusters. So I mentioned that globular clusters are relatively simple stellar populations. And the reason the word relatively is there is actually they vary in light elements. So they have subpopulations that vary in elements such as helium, oxygen, sodium, and so on. And the way that we classify these subpopulations is looking at the sodium-oxygen anticorrelation. And I show that in the inset of this plot. This is CMD for M4, and the inset is showing the sodium and oxygen abundance space. So using the notation SP1, which stands for subpopulation 1, and SP2, SP2 stars, sorry, the formatting's messed up a little bit, but SP1 stars are lower in sodium and higher in oxygen, and SP2 stars are higher in sodium and lower in oxygen. You can again see that in the inset. So we know from stellar evolution theory that different initial helium abundances are going to lead to mass differences between the subpopulations. So for SP1, they are lower in helium but higher in mass, compared to SP2 stars, which are higher in helium and lower in mass. Because of this, we actually expect to see a bimodal mass distribution when looking at the masses in different evolutionary phases. Something else that's theorized is mass loss differences between the subpopulations. So some models have shown that SP1 stars will have less mass loss compared to SP2 stars. And this is something that I wanted to test with my asteroseismic mass distributions. So I'm only going to show my results from one cluster today, but it is the most exciting cluster. This is the mass distribution for my cluster M80, where I show RGB masses in red and early AGB masses in green. So one thing you can see is that in the RGB, we only are detecting one peak. And that's because the mass difference between the subpopulations on the RGB is quite small. So it's actually within our uncertainties. However, in the early AGB distribution, we clearly detect a bimodal distribution, which is very exciting to see. So to investigate this a bit further, we fit a Gaussian to each of those peaks and took the mean of the Gaussian as approximate subpopulation masses. And then similar to what we did before, found a mass loss for each subpopulation by finding just the mass difference, or the mass difference between the RGB, or the average RGB mass, and the two subpopulation masses on the early AGB. And we quantified a mass loss for subpopulation 2 stars, or the mass loss for subpopulation 2 stars is a factor of 2 larger compared to subpopulation 1. So this is could be the first direct evidence of different mass loss between the subpopulations. And one thing I did want to point out, the plot that I showed before only used the subpopulation 1 mass loss, and that's because SP1 stars are meant to be more abundant within clusters. However, it introduces another caveat. On top of needing a mass loss metallicity trend for type 1 and type 2 globular clusters, we might also need, or subpopulation 1 and subpopulation 2 stars might also need their own mass loss metallicity trends. However, we can't, so this is just tentative evidence. To actually confirm it, we require spectroscopic measurements of our entire sample to classify our stars into the subpopulations. So we need to look at that sodium-oxygen anticorrelation. But if we do see that subpopulation membership correlates with our bimodal mass distribution in the early AGB, this would be the first direct measurement of a mass loss difference between subpopulations. So it could be a very exciting result. So I'm just going to leave my summary up, but thank you for listening.
Yeah, thank you very much for your presentation. So I have a mixture between a comment and a question, which is, as far as I understood, you are using scaling relationships for the mass determination. So I do not agree with the fact that you are calling your mass loss prescription like model independent, because it's based on a model, which is the scaling relationship, which is a simple model, but still a model. And it's a model that is known to have systematic effects for different stars because it's based on a kind of dimensionality argument. So have you checked whether this mass loss, integrated mass loss that you're getting is still there when if you use, or how much does it change when you use a grid-based asteroseismology?
I haven't checked that.
Okay.
We have, for one of my clusters, we did check or did make a comparison between the integrated mass loss we measured and a Reimers mass loss scheme, and basically found what Reimers mass loss scheme would equal the amount of mass loss on the RGB as...
Yeah, but my point is in a slightly different direction. Is the theoretical framework to get the mass, which is how you get the mass just directly from comparing with the prediction of, the large frequency separation, and that models predict, not scaling relationship, but detailed numerical models. Because this is usually done also in the field.
I mean, short answer, no, we haven't done that.
No, thank you.
So definitely something you can try in the future.
How do you know that the two populations are the same population? Could it be that one is systematically more massive?
What do you mean by the same population?
Well, by saying that the mass loss is delta M, you're assuming that the one with a more mass eventually, on average, will lose that amount of mass, which means it's the same guys, right? What if they're just different masses?
Well, ultimately, there is a lot of assumptions in this work, and I don't think I can answer that until we have the chemical abundances. We actually need to figure out initially where the stars sit in our mass distributions before we can possibly make more stronger claims about this research. But there definitely could be kind of mixed signatures that I don't know if we are able to detect with asteroseismology masses.
Hi, Maddie. I know that one of the major problems you've had with this is dealing with K2 data.
Yeah.
Do you have any plans and or interests in the future of doing something like a dedicated study of some globular cluster where you hog some telescope time and you stare at a globular cluster for a long time to get actually really nice looking asteroseismology?
That would be amazing. That is like my dream goal after my PhD is done, future postdoc or something. Haven't got any plans, haven't looked into any potential telescopes. As I mentioned, the Roman Space Telescope could get higher quality data that we could do asteroseismology on for globular clusters. So that could be an exciting potential. But besides from that, probably need to do a bit of research to see what's up and coming as well.